Greetings and welcome, friends. Today we're talking about roots and zeros. Roots, zeros, x-intercepts, solutions of quadratic equations, polynomial equations, all somewhat synonymous with one another. So, roots and zeros, rutabaga, here we go. We're talking about the fundamental theorem of algebra. Fundamental, it's like core to the concept of all of algebra. By the way, there's also a fundamental theorem of calculus that you may someday learn. So let's read what this fundamental theorem of algebra says. It says every polynomial equation with degree greater than 0. So let's say I had a polynomial like f of x equals x to the 7th plus blah blah blah, right? What's the degree of this polynomial? 7. They are saying with degree greater than 0, all right, it has at least one root in the set of complex numbers. What's the set of complex numbers referring to? Complex are numbers of the form a plus bi. All right? If b is 0, then this whole thing's 0, and it's just a real number. If a is 0, then this whole thing's 0, and it's just a purely imaginary number. But complex numbers are those kind of hybrid either case situations. Now, so what they're saying is, if you have a degree greater than that, then you have at least one root. All right? One root. All right, greater than one root, technically, right? Greater than or equal, I guess, is what it's saying, which isn't really all that thrilling. You know, for a fundamental theorem of algebra, you'd figure it would have been something cooler than that. But it's core in understanding some of these future concepts that we'll be looking at, and its buddy, the corollary to the fundamental theorem of algebra, is even more powerful. Are you familiar with what a corollary is? No. A corollary is not, this isn't a definition. This is a corollary is a follow-up to a theorem. Okay? So you might have seen some of these in geometry. I can't think of any corollaries right now. But there might have been like a corollary to the triangle sum theorem, and it would have said some other follow-up information, blah, 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 right? So a corollary is like a follow-up theorem that it's kind of like not that big of a leap from one to the other, but it itself is still no less powerful. Now in this case, this corollary is actually way cooler in my mind than the fundamental theorem of algebra, but it couldn't have existed without it, okay? And it's kind of like, it reminds me of when Isaac Newton said that, in reference to the discoveries he made, that he made them while standing on the shoulders of giants, is what he'd said, right? Basically, he found out calculus as a result of being aware of all of the mathematics that other people had already discovered, right? He just took that one little step past it, is what he, in his humble way of claiming that, said, right? And that's what this corollary does, is it kind of like is one step beyond this theorem. And it says that a polynomial equation of the form p of x equals 0 of degree n, right, so we're getting specific now, with complex coefficients has exactly n roots in the set of complex numbers. So this one said there's at least one. And it's like, okay, thanks. But this one's, the corollary is going even further, saying, no, tell you what, if your degree is n, you have exactly n roots in the set of complex numbers. All right? So in the case of this little example, mini example here, I would say that has exactly 7 roots. Now, not all of them are real. Okay? It doesn't mean it has 7 real x-intercepts. Some of them could be imaginary, okay? But we're saying it definitely has 7 no matter what, all right? And this is very powerful. It allows us to, with confidence, when we're searching for the roots of a polynomial equation, we can say, oh, I'm done, right? I've only got I've only got 7. Once I found 7, I can stop looking, is the idea. So let's do an example, applying some of this stuff. And this is what we got. Let's say I have the polynomial equation x cubed plus 3x squared minus 10x minus 24 equals 0. And I'm looking for the roots. So suppose I have this polynomial equation, and I want to find the roots, the zeros, the x-intercepts, right? How many does this have? 3. How do you know? Because it's the degree right there, right? And based on this corollary of the fundamental theorem of algebra, I almost said calculus, we know that it has exactly n roots in the set of complex numbers. Now, if I wanted to find those roots, all right, well, actually, let's make our claim first. We know that it has exactly 3 roots. Right? Some of them might be imaginary, though. So that's a thing, but that's fine. So if I wanted to find those roots, let's set up a table of values, and we're going to start picking some. I guess I could call it x and y, or x and f of x, right? So I'm gonna plug in like -5 and -4 and -3 and so on, and I could actually do some synthetic, division for some of this stuff, right? So let's do some scratch work on the side. So if I want to find out -5, I could do some synthetic substitution, right? And I'd divide that into 1, 3, -10, -24. There's no placeholder. I'm good. And I would do this, bring down the 1, -5, and I'm going to cruise through this. Actually, I'll do this in yellow.
Why would you get -5?
Because I'm inputting this, so I'm just finding the output. So I bring down the 1, the -5, -2, 10, 0, 0, and -24. So the fact that that's a -24, that means that is going to be the output for that particular point, right? And I could go forward and plug in a whole bunch. And what would I be looking for if I'm looking for roots? I'd want ones that have what as a result? I'd be looking for ones that give me 0 as their outcome. And that's what we're going to do, but I'm going to show you a different table that's going to, bless you indeed, that's going to kind of be a bit of a, well, we're doing the same work, we're just writing less of it. All right, and this is the idea. I'm going to write this table like this and like this. And here I'm going to put my synthetic division stuff of the 1, the 3, the -10, the -24. Right, and I'm going to put the -5 here, I'm going to put the -4 here, and I'm going to keep going in a minute. But what I'm going to do is synthetically divide, but I'm not going to write this whole row of work. I'm going to do this row mentally, all right? And we're going to get really good at this over time, so we'll be awesome. So here we go. So for 5, for instance, the first thing I would have done is add the 1, right? So I would have added the 1. And then I'd do -5 times 1 is -5. And in my head, I'd be thinking -5 plus 3. I wouldn't write down that -5, but that's what I'd be thinking. And -5 plus 3 is -2, right? Because of the more influential. And then I'd multiply -5 and -2, and I'd get +10, and I'd be thinking 10. I wouldn't write it. I'd just be thinking it. 10 and -10 is 0, right? And then -5 times 0 is 0. And -24 plus that is -24, right? And I would know that this is my output right there, right? So I mean, even if you wanted to kind of do something like that, you could, right? And I'd say, well, that's not an x-intercept. I'm going to keep looking, right? And now I'll try the 4. So it's just going to save me some space, and eventually I'll get really fast at this. So here we go. Bring down the 1. -4 times 1 is -4. Plus 3 is -1. -4 times -1 is +4. With a -10, +4, difference is 6, but the more influential one was 10, so it's negative. And then to multiply -4 and -6 is +24, which when I add to that is 0. Ding, 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 ding. So I found one. Good news. So we just found one of our roots, and it happens to be a real one, but it is definitely a subset of the complex numbers. So I could say up here, like, x equals -4 is one of mine. And I'm expecting 2 more that I'm looking for, right? because I know it's going to have at least 3, or exactly 3, not at least. Exactly. Now, so let's keep looking here. So I'm going to extend this little chart, and I'm gonna end up, let's see, -2, -1. We'll keep going for a while here. Here we go, and I'm looking for 3. So let's see. Bring down the 1. -3 and 0. -3. 0. 0. -10 is -10. 30. Positive 30 and -24 is positive 6. Yeah. Well, that's a no-go. Let's try -2. Bring down the 1. -2 times 1 is -2. Plus 3 is 1. -2 times 1 is -2. With a -10 is -12. Ding, 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 ding. I found another one. Good news, friends. Good news. So my other one is -2 so far. Now, I completely randomly picked to start at -5, okay? So eventually we'll have some better tactics for narrowing down what we should start practicing or trying our attempts with, but let's see. Let's try bring down the 1. -1 and 3 is positive 2. -1 and 2 is -2. It's -12. And that's positive 12, and that is -12. So that's... Now think about these. This is... Remember, thinking about this as synthetic substitution, that means there was a point at -5, -24, at -4, 0, at -3, 6, at -2, 0, and so forth. So think about this graphically. These were my y values, right? So I graphically could think about this as, if I wanted to visually be imagining this, I was below the x-axis at -24, then I hit 0, then I went up to 6, then I hit 0, and now I'm down at -12, right? So I'm looking for the next time I know it's gotta come back up, all right? Actually, the graph is probably more like this because it's a 3rd degree, right? So I know the graph has got to come back up at some point. So that's what I'm going to be watching for. All right, so visualize that sort of concept when you're doing this. So right now I'm below the x-axis by 12 units. So let's plug in 0. So bring down the 1. 0 and 3 is 3. 0 times 3 is 0. Plus -10 is -10. 0 times -10 is 0. Add -24. Oh, man. So I'm going further below the x-axis. But remember, I'm looking for the ones that are 0, so I'm getting further from 0 right now. So I might even say, well, I could try 1 next, but I'm getting far away. Maybe I should skip 1. Maybe I should try plugging in like 2 or something and see what happens, or 3 and see what happens. For the sake of our practice, I'm going to keep going, but we'll talk about those strategies of skipping. On the homework, you can definitely skip around as you need to a little bit. But do it intelligently, right? Don't just like look at the answers and then be like, oh, I'm just only going to try those ones. That would be not any learning gained from that, really. So here we go. Bring down the 1. 1 times 1 is 1, plus 3 is 4. 1 times 4 is 4, plus -10 is -6. 1 times -6 is -6, plus -24 is -30. Oh, man, guys. All right, what are we going to find here? We're getting further away. Let's try 2. All right. All right, here we are. I guess I still need this insight, don't I? Bring down the 1. 2 times 1 is 2, plus 3 is 5. Aha. 2 times 5 is 10, and -10 is 0. 2 times 0 is 0, -24. Now, wait a minute. Guys, why am I optimistic here? Well, I was going down, 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 and now I'm increasing. So that means I'm getting closer to 0. In fact, because I'm increasing, I can actually analyze this and be like, there's been a bend here because there's a change in direction. That's one of my local extrema, right? And that would be worth knowing. So, so I'm getting closer to the x-axis now. This is good news. So let's plug in 3. So 3 times 1 is 3. With a 3 is 6. 3 times 6 is 18. Wow, brain fried. And -10 is positive 8. 3 times 8 is positive 24 with a -20. We found it. We did it. We did it. So let's see, our other 0 occurs at 3. Okay? So, so the things that I want to recommend when doing this, all right, yeah, it's definitely like just guessing and checking, but we can be smarter than that, right? I can analyze, all right, what's going on. Okay, so, you know, below the x-axis, I hit it. Above the x-axis, I hit it. Below the x-axis, I changed direction. But when this was getting lower and lower and lower, all right, maybe even after this, I might have just been like, I'm going to skip to 2, or I'm going to skip to 3. All right, suppose I skipped too far. Let me just do 4 for fun. All right, maybe it's not that fun to you. You don't have to write this one down. 4 times 1 is 4 plus, what was this 3 up there? Is 7. 4 times 7 is 28, and negative 10 would have been 18. 4 times 18 would have been 40 plus 32, 72, and negative 24. What's that? 52 minus 4, negative, is that positive 48? I think something like that, right? So if, let's say I skipped from here to here, all right? And the two outputs I would have been looking at would have been this one and this one. When I got that result, what would I have, why would I have known to go back to try something in between? How do you know it passed through 0? Because the sign changed, right? So we can use our same strategies and tactics from last section while doing this, right? So I see the sign. So if I jump too far in my ambition, I can be like, oh, I clearly missed an x-intercept between there. I'm going to go try another one, right? And then I would go back and try the 3 or something like that. So I just want to point out, you could have tried those fewer ones. Another trick, all right? So let's see. I guess here's my tricks. All right. One, I said, let's see, skip inputs when it's getting further from 0. Farther from 0. Step 2, all right, is if you're too ambitious, if you're too ambitious in skipping inputs, then for trick number 2 is pay attention to sign change. So if you skipped too far, you'd know to go back. Now if I skipped way too far, all right, like what if I skipped from -5 all the way to -1? I would have just been like, oh, negative to negative, nothing happening here. But I actually would have skipped too far, and I would have missed 2 zeros in the process. All right, so you don't want to necessarily skip ahead too much, but just be aware of that. And then trick number 3, ready for this? This is going to save us a lot of work. Use depressed polynomials. Okay, now I'm going to show you that tactic right now. When I had found my first 0, I didn't have to keep using this, right? I was using the original polynomial. I was having to do a whole other column of work this whole time. All right, it doesn't sound like a lot, I suppose, but what I could have done is started using this as my polynomial, right? Because those are the coefficients of my depressed polynomial. And what does my depressed polynomial have in common with my original? I know that it has the 2 other remaining roots that I'm looking for, right? I just found -4 belongs to this guy, and I'm looking for 2 more. Turns out if I plugged in -2 and, what was it, 3? Yeah, if I plug in -2 and 3 into this guy and synthetically divide, those will still give me 0. Right? So I could actually have, at this point, let's see, where am I here? Oh, I was getting a little bit of lag there. All right, good. So what I could have done is I could have taken the 1, -1, -6 at that point, and let's just do like a break off, and assume that this is what we did instead. So what I could have done is started an entirely new chart, and I wouldn't actually go down that low just in case, what was it, 1, -1, -6. And I could have actually started guessing some other values here. So I just plugged in -4, so I would have tried -3. Right? And I would have done 1. Let's see. Here we go. 1, -3 and -1 is -4. -3 times -4 is +12. 12 and -6 is +6. Now notice, this is not a 0, but what's the deal here and here? Oh, wow. Actually, that's really unusual. Huh. Well, my counterpoint ended up coincidentally being the same. Typically, your depressed polynomial will not have the same outputs as your original other than its x-intercepts. Okay? Those are the only ones I'm actually expecting to work out that way. All right, so I would have kept going, right? And then I would have done 1 and -2, and that is -3. That's +6 and 6, and that's 0. Right? So I would have found that. And then I would use this depressed polynomial. Right? So I could have done 1, -3, set up my little chart, and I've already tried -3, -2, then I would have tried -1 from here, and so on and so forth. Right? So you could use that as well. All right? And then the fourth trick I might recommend is once you have a quadratic for your depressed polynomial, quadratic depressed, just try factoring it. Right, to solve it, right? Or I guess instead of factoring it, I could just set it equal to 0 and solve. All right, set the g of x, maybe I'll write that with color. So I could have just taken that g of x equals 0 and solved from there. So the other alternative was I could have taken my depressed polynomial, this guy. I knew that was a quadratic because there's only 3 terms in it, and that's x squared minus x minus 6. Right? Maybe I'll just show that right here. So I would have taken the x squared minus x minus 6, set that equal to 0, and then solved. In this case, it's factorable. I would have factored it to x with a 2, x with a 3. Right? And it would have been -3 plus 2. And then I would have been able to solve each of those. Right? So I would have gotten the same answers. So all sorts of little tricks that you can do to try to make this easier. That'll help out over time. But at this point, what we're doing essentially is I'm making a table of values and I'm finding the values using synthetic substitution. But we're skipping one of our entire rows from synthetic substitution just to try to make things a little bit easier and faster. And now that we know how to analyze all of this stuff, we're really good. Question, comment? Yeah, we've got another 12 minutes. Yep, you're good, you're good. So let's look at one more concept, and I'm going to get as far as I can on it. And this is called the complex conjugates theorem. We don't technically have any of these problems on our homework tonight, but I'm going to get done what I can get done. I chose to give you easier problems tonight, ones like the first example we did, basically. So let's see. Suppose A and B. A and B are real numbers. With B not equal to 0. Ready for this? If A plus BI is a 0 of a polynomial function, then, get ready for this. Let's see. The name of this is complex conjugates theorem. You might be able to predict this based on the name. Then a minus bi is also a zero of the function. Okay. So what this is saying is when we do have a zero that's partially imaginary or all imaginary, right? It said b cannot equal 0. A could have been, right? That if you have one complex 0, you automatically have two complex zeros. All right, the way I think about this, if you, this is Wadi thought, if you have an imaginary friend, then you also have an imaginary enemy. Right? That's the way I think about it. Right? So if I have an imaginary friend, I have an imaginary enemy. It's my little way of remembering this. So let me show you how this is helpful to us. Here's our example. Let's see. Suppose I have the polynomial f of x equals x cubed minus 5x squared minus 7x plus 51. All right. And I tell you, find all zeros and that 4 minus I is a 0. All right, or given maybe that 4 minus I is a 0. That might make more sense. Given 4 minus I is a 0. So here's the idea. If 4 minus I is a 0, what do you automatically know? Therefore, 4 plus I is a 0. And how did you know that? The complex conjugates theorem, right? Why is it complex conjugates? Because this is a complex number, that's a complex number, and these are conjugates of each other. They're not opposite. They're just, the middle signs are different, all right? So, so this is the idea. 4 minus I is a 0, therefore 4 plus I is a 0. Here's my setup. So I'm going to, step 1, find the depressed polynomial that has those as its zeros. Has the complex zeros. All right? And that's going to be an interesting little maneuver. Then step 2, I'm going to long divide the original polynomial by the depressed. So I'm going to long divide, I'll say f of x by g of x. Okay? The result is, all right, now g of x will contain these two zeros. The result is going to be another depressed polynomial that contains the zeros that I don't know of yet. Okay? So step 3 is find the remaining zeros in your new depressed polynomial. All right, and I might call that one h of x or whatever. Right, so f of x divided by g of x gives me some value. What it gives me is another depressed polynomial that contains the missing zeros I'm looking for, is the idea. So how do I find the first depressed polynomial is the question. Well, that's actually got some interesting maneuvers. This problem is going to go past the bell, just so you know, or the end of class. So be ready. We've still got 6 minutes, so don't pack up. Just write down as much as you can and quietly sneak out of the room when the time is good. So here, let's find the new depressed polynomial. So if 4 plus I and 4 minus I are zeros, now guys, what about this? If I told you,
Attention, there will be no use of the gym at lunchtime. It'll be closed.
if I told you that x plus 3 is a factor, what would you have told me its 0 was? X equals negative 3 would be the 0. If I told you 5 is a 0, what could you tell me a factor was? X minus 5, right? Remember, it's always kind of the opposite. The opposite of your 0 is the number that goes with the factor. So if I say 4 minus I is a 0, then that means, ready for this? My depressed polynomial for one of its factors must have an x minus 4 minus I as a factor. All right, it's kind of weird looking. And if 4 plus I is a 0, then x minus 4 plus I is a factor. Does that kind of make sense, roughly? Ignoring all the imaginary parts? All right, like if I told you that this was x minus 5 and x plus 10, then you would have known that, oh, my zeros were positive 5 and negative 10. So I'm using that same sort of concept, but this time with imaginary things. So let's do this out and see what happens. So this is equal to, let me distribute this minus sign here for both of these. And right? So I'm going to have, for this, x minus 4, and minus a negative I is the same as plus I. And for this one, I'm going to have x minus 4, and instead of plus I, it's going to become a minus I. And what I'm going to do to figure out what g of x looks like, if I FOIL, well, I can't FOIL it because it's a trinomial times a trinomial, I guess, in some ways. I'm going to have to triple distribute this in order to figure out what g of x originally looks like. And there's going to actually be, I might have to back up this equal sign here because it's going to have 9 terms here coming at you. Here we go. Follow along. X times x is x squared. X times negative 4, it's negative 4x. X times negative I minus ix. All right? Now let's distribute the negative 4 part to all of those. Negative 4 times x is minus 4x. Negative 4 times negative 4, plus 16. Negative 4 times negative I, well, negative times a negative is positive, so plus 4i. And now I have to distribute the I to all 3 of those, right? So I times x is plus ix. I times negative 4 is minus 4i. And I times negative I is negative I squared. Now watch how cool this is. Ready? Look at this negative ix. What does that combine with? Positive ix. Those just cancel out. Positive 4i and the negative 4i cancel out. Wow, that's really nice so far. Let's see. I'll be able to combine this. And the 16 and the I squared. What is I squared the same as? I squared is negative 1, right? And then minus a negative 1 becomes positive 1. So what this simplifies down to be is g of x equals x squared minus 8x plus 16 and 1 is 17. All right. And the fact that this had imaginary outcomes, I would have expected that this would have been a semi-non-factorable problem, right? Technically, it's factored up here, but they're not that nice. So that was step 1. All right. We don't have any problems like this on homework. Just, it's going to be tomorrow's homework that has this and some other concepts. Now I found this depressed polynomial. If I divide my original polynomial by it, I'll get the other depressed poly that has the missing roots. So here we go. I'm going to set up this long division. What's my original? X cubed minus 5x squared minus 7x is going to be my dividend. And notice I can't do synthetic division because this is not a linear binomial. So that's why it has to be long division. Minus 7x plus 51. It's all coming back to us. So here we go. X squared minus 8x plus 17. And let's long divide. Long division. Here we go. So divide leading term by leading term. It's x squared. We're masters at this, so I'm going to move through quick. Multiply. Oh, no. It's not x squared. That's x. Aha. X cubed divided by x squared is x. And there I am saying I'm a master. So x times x squared is x cubed. X times negative 8x is minus 8x squared. X times 17 is plus 17x. Subtract step. Bam, bam. That's going to be 3x squared because of the double negative. And that's going to be negative, what's that, 24x. And then bring down the 51. Right, and we'll divide again, leading term by leading term. And that's going to be plus 3, apparently. Let's multiply this out, see what happens. Now, what am I expecting as a remainder? I'm expecting this to be 0 because I anticipate that this is a factor of that because it contained the same roots that it had. Okay, so this better equal 0, otherwise I messed up bad. Here we go. 3 times x squared is 3x squared. 3 times negative 8x is negative 24x. 3 times 17. I know we want it to be 51, but is it? It is 51. How wonderful. Subtract that, and it equals 0. So that means h of x, my other depressed polynomial, is just x plus 3. All right? No guarantees this will always be linear. For instance, if I started off with a quadratic, a quartic, this would have been a quadratic or something like that. But here we go. Step 3, find the remaining zeros in your new depressed poly. Well, that one's easy in this case. I'm just going to take x plus 3, set it equal to 0, and solve. Minus 3, and I'm going to get x equals negative 3. So that means, what were my zeros for this function? X equaled 4 minus I, 4 plus I, and negative 3. It had exactly 3 roots, just like the corollary to the fundamental theorem of algebra said. 2 of them ended up being complex, but that's fine, But there were exactly 3 of them. All right? So we'd found the depressed polynomial that contained those 2, divided by it, and then found the other depressed polynomial that contained that one. By the way, you also could write this as 4 plus or minus I, comma, negative 3, if you didn't feel like rewriting that multiple times. So there's the lesson, folks. Thanks for watching, and have a great day. Bye-bye.